about testing a lot, all the time. But what does it mean to test software architecture? Because we test code. But I create an architecture. Should I test it? Yes. Well, what does it mean to test an architecture? This is what it means. So let's take a look at this image. And what you see on the screen here is a road. It's a bridge crossing over a river, connecting two sides. And that bridge, let's say, represents our architecture. It's the structure. And the cars going across there represent requests going through the system. Okay, so there's our analogy. Is this structure suited for the amount of traffic here? Sure, I'd say that's fine. But what happens? Like our systems, towns start to grow. And over the course of several years, this is what that, now this was working perfectly before. I bet it's the microphone. This is exactly what that town looks like now. Or let's say in 30 years, or 30 years later. Notice it's the same bridge, but look at how much traffic is going across it. Is this structure that we created still suitable at this period of time? Probably not. Because if we don't pay attention to the structure of things, our architectures, this is what's likely to happen. And we don't want this to happen to our systems. These are when systems just stop working, they fall apart, they implode. This is what it's about on testing software architecture. So that was our system, it just crashed. But we still haven't answered. What does it actually mean to test software architecture? Well, I could talk about a lot of abstract ideas, but let's use a real example. And so here's going to be our example. This is a student test-taking system. Now, what this system does is students all around the country will take standardized tests, the same test, to be able to assess how the school district is doing, or the school is doing, or the teacher, or maybe the students. And so this is all an online test. Students come to their classrooms, and they sign in, they take a test. So let's actually see kind of the flow of this. Because students have to sign in. Well, we should probably test this. Yeah, let's do that. Let's test this. So here is a test case for student sign-on. So we're going to unit test this. Let's do it. Okay, so we're going to test this. So what we're going to do here is run a little bit of Python, and we pray to the demo gods. Go. And it completed. Cool. We do this all the time. This is testing. We understand this. As a matter of fact, I do have to, a lot of us just saw Venkat. I do have to channel Venkat, because here's the reason. He has this great quote, and I love it. He says, testing is like exercising. We know it's good for us, we know it's healthy, and we know usually it produces good results. But how many of you like to exercise? No. It's a perfect analogy, isn't it? We know we should do it, but we don't like to do it. But anyways, so this is fine. Now, let me show you the architecture for this system. And here it is. It's a microservice architecture consisting of a lot of services that render up tests and have its own database. This is the architecture for that. Well, we just tested the sign-on and some of the code. But how do we test the architecture? We don't have source code here. There's lines and boxes, components, services, databases. That's what we're going to find out in this session. Okay, so it turns out that what we're really looking for here is what's called structural decay. Just like those bridges, buildings, if you walk along and you'll see a concrete pylon holding up a bridge or maybe a side of a building, and you look closely, you'll always see cracks in that pylon. Sometimes maybe even big seams like this, but there's always little cracks. That's structural decay. And if we don't pay attention to these actual physical buildings or bridges, they're going to come crumbling down, just like that bridge I showed you. That's exactly what happens with architecture. That is the structure of your system. That's what we're looking for. Structural decay. So let's find out how to test it. It turns out that there's two types of ways of testing a software architecture. There we go. Okay, so when we test a software architecture, we can look at two aspects to learn how to test it. Is the architecture okay? Well, first are the operational characteristics associated with those. Well, things like scalability. Does it scale? Does it perform? Is it available as it should be? But then there's also the structural integrity of that system. Let's see how to test each of these and also what they are. So we're going to start with looking at first the operational characteristics. But regardless of those, each of these two kinds of tests that we're going to be writing, we're going to be writing architecture tests in this session. Two different kinds. So we're asking three main questions. We're constantly changing the functionality, our source code. Are any of those changes to the functionality or adding functionality, are those impacting the architecture, the structure? The second question, are changes to our environment impacting the architecture? Maybe we are moving from on-prem to cloud, cloud back to on-prem, which does happen, by the way. Or maybe it's just moving to a different platform, a different server, a different kind of environment. Does it impact the architecture in any way? And also, number three, you say the system scales. Oh, yes, that architecture I just showed you will scale. Yeah, can you prove it to me? Can you demonstrate that that actually scales to what we need to? We can answer all of these questions through these tests. Okay, so let's actually start by testing an architecture from the operational characteristics part of it. Okay, and we'll do both of these. Now, when I say operational characteristics, I'm really talking about these kind of things. Things like performance, responsiveness. Is it secure? Can we demonstrate recoverability, elasticity, data integrity? Is the system reliable? We could test and verify all of these things to see if the architecture is structurally sound. Interesting, though, I think we can all agree we can find ways of testing performance. How do you test reliability? Think about that. We have to demonstrate a reliable system. We have to have reliable systems. Is your system reliable? Yeah. Can you show me? No. Because, why? I don't know what it means. We know what the word reliable means. But how do we measure that? How do we define what that means? So if we were going to show and test that the system's reliable, what might you possibly do? About this, any ideas? What might you possibly do to test to see if the system's reliable? Good. Okay, so I've heard a bunch of good answers here. Yeah, is it available? I go to use the test system, this student testing system, and it's down. Well, it's not very reliable. Yeah. Or I'm using the test system, it was somebody else I think mentioned, I'm using the test system and all of a sudden it crashes right in the middle of a test. What's my trust of that system now? That I'm going to go back and restart the test. Oh, it's probably going to crash again. Yeah, these are good ways of identifying that. What if I answer a question and all of a sudden, or do the whole test of 100 questions as a student, and I come back and my grade says, well, you didn't answer 40 of the questions. Yes, I did. No, you didn't. There's 40 answers you never submitted. No, I did. That's all about data integrity. Isn't it interesting? Here is the key point in any characteristic you make up or encounter or identify. Here's the magic. If you can measure it, then you can define it. That becomes our definition of reliability. And if we start to think, yeah, I need to measure it, I need to demonstrate it, all of a sudden now, guess what we have just done? We've just defined what reliability means for us. Data integrity, fault tolerance, availability, maybe performance. Maybe this has to be fast and it's erratic. Sometimes, I was trying to upload the slides during Venkat's talk, by the way, but I would get about 80% upload and it would say transfer failed. I'd restart it and it would go really fast and then just kind of stop and say 56 minutes remaining. Yeah, it wasn't very reliable network, is it? Because yesterday it was fine. So I will, between my two sessions, I will make sure that these slides are uploaded, as well as the last ones for decomposition. But this is my point. We can now define what that actually means. And now we can demonstrate it, make sure it is reliable, and test it. Cool. Okay. How do we test these? Through something called fitness functions. Now, these were first introduced in the book by Neil Ford and Rebecca Parsons and Patrick Quah called Building Evolutionary Architectures. This is a picture of the second edition, but this was the book they were first introduced. An architectural fitness function basically is an architecture assessment of some objective, that means measurement, objective integrity assessment of some sort of characteristic, something we can measure and demonstrate through metrics. That's what a fitness function is. Okay. This has its roots from engineering, as a matter of fact. Bridges, aircraft, all use what are called fitness functions. Every time we add, oh, there's so many jokes I could say about this. The structural integrity about an aircraft. Jets that we fly are designed so that those wings, believe it or not, can actually bend to almost 80 degrees. So if you see the wings flapping like this in turbulence, yeah, don't worry. They can actually go all the way up to here. They measure that and verify that through something called a fitness function. And so, of course, our favorite airline decides, we want to add 3 more rows. And so we're going to squish down already the small legroom and add 3 more rows. Well, what's that going to impact? The overall weight of that aircraft. So how does the aircraft manufacturer know that that's okay? Can I add 3 rows, 3 more rows? Because that's 18 more people, plus their luggage. What do? They execute a fitness function. They add the rows, retest the wings, and it's like, nope, the wings only go to 70 degrees now. Can't do it. Fitness functions, that's where they come from. So let's see how to write these. What does a fitness function look like? Well, there's a lot of tools out there, of course, that already do this. They gather metrics and measurements. Sonar Cube, Sonar Graph, all these many tools that exist in our environment. Those are useful to a certain degree. Because what they're telling us is a point in time about, is their system scaling? Is it available? But we don't have to always use these tools. Now, I do leverage these kind of tools if I can extract the information, because it does us no good for a co-radiant screen to be way up on the wall there and say, oh, look, our servers are going down. Yeah, okay. I wish I would have known about that, because now I'm just visually looking at it. I want to programmatically have that data to measure trends. So what we can do, and in most cases I do, write fitness functions myself. And let me show you what those look like. So for example, I could take my application, my user interface, my service, any system or any component, and I can do what's called observability. In other words, what information is important to me? Maybe it's response times. Maybe it's uptime. Any kind of metrics. Maybe it's the number of concurrent requests I'm accepting. And I can stream that to something, let's say Kafka, which is a great tool for doing this, by the way, because of its high throughput here. And if I miss a particular metric, I don't care. In the next couple of milliseconds, another one's going to come through. That's fine. It's really nice for that. Then what I do is I write a microservice, capture service. I say a microservice, but what this does is it captures that information. I write this, put it in a container, drop it into production, and this is now capturing those raw metrics as a subscriber to the Kafka topic. Now, I'm just saying Kafka. It could be a message queue. It doesn't really matter. But it is asynchronous. So I'm now capturing all the raw metrics. I then write another service, and this is the fun code right here in the analytics service, because what I'm doing now is reading that raw data and I'm analyzing it. I'm using maybe basic machine learning analytics, basic mathematics to start measuring trends or thresholds that are occurring. And if I'm measuring, let's say, a trend or saying no trade can't exceed 40 milliseconds, if it is, then notify me. If all of a sudden I start to see we're no longer scaling, notify me. All this runs in production behind the scenes. I am now analyzing and measuring my architecture for structural decay right here on stage right now, because I have fitness functions running in some of the systems I work on right exactly now. And it's measuring. Now, I hope it doesn't notify me or else I'm going to have to go. But that's the whole idea. Okay, there's two types of fitness functions we can actually write. The first type are really those trend-based. I'm a big fan of trend-based fitness functions. What these do is measure a trend of something over a certain period of time. We just did a deployment, and I'm measuring the trend of scalability. Over time, does our system still scale? Is it going up? Is it going down? The reason I'm a big fan of trend-based is because the other kind is threshold-based. And unfortunately, a lot of times servers do go down. A lot of times our cloud vendors have issues. And all of a sudden it's a hiccup in the system. Let's say I'm measuring performance. And all of a sudden now it goes skyrocket high. I don't want to be notified. I already know we have a server problem. I want to measure the trend of that because that's not structural decay. It's another kind of problem. But both of these do exist. Okay. So when should we actually do this then? In other words, should we test our architecture through something called triggered fitness functions? Now, these are things that are triggered. These are tests that we write that are triggered during our CI/CD pipeline, during our deployment or release. Or should they be continuous fitness functions? Those that are just like I described, running in production right now, just continually measuring trends to see if things are getting better or worse over time. Okay, so when should we do this? Oh, yet another decision we have to make, huh? Well, let's try to analyze each of these and see what they are. Because with a triggered fitness function, before we release that software, we see, whoops, that's going to impact our responsiveness. That change that we just did is going to impact scalability. These are basically like load tests that we run. Well, load tests. It depends on what we're measuring. We might be measuring availability. We might be measuring reliability, recoverability, any sort of characteristic. That's the good part. The bad part about these is the fact that we have to maintain all of those tests. Worse, we have to maintain all the data used to execute those tests. Who wants to do that? Please, no. That's like a prison sentence. Yes. If you fail the build, you're responsible for maintaining all the data for every one of our scalability tests. No, no thank you. This is horrible. Every time we make a data change, guess what gets invalidated? All of our fitness functions. We have to maintain those as well. But it gets worse than that. Because with a triggered fitness function, what we're doing is we're simulating user behavior, aren't we? We think we know how the user is going to use the system. No, we don't. Do any of you remember the days of Power Builder? This goes back many, many years. This is now we're talking in the 90s. This was a 4GL language. And it was, I used Power Builder all the time. We had a particular system, and it was a call center application written in Power Builder. We went through all of our testing. This was a good system. And so we deployed it at the call center. And sure enough, we had a user call and say, system just went down. Like, what? We're looking through all the logs. We're looking and saying, we can't repeat this error. Must have been a glitch. Every day, this particular instance that was on this one caller's desk kept failing. We spent weeks trying to simulate it. Weeks. Couldn't figure it out. So we did the smart thing. We quit and moved to another system company. No, what we did was we shadowed the user. Because clearly you're doing something we're not doing. So, colleague and I, we shadowed the call center user, and we're watching her work, and she's working, and we're like, this is fine. And then we heard the call. So what I'll need you to do is verify something. Okay, well, let me go get that. That'll take a while. Okay, I'll stay on the line. And then she did this. She was I don't have my monitor back up. She was doing this with the cursor. Had the mouse, and she was kind of like drawing all over the screen and all this kind of. She was bored. So she's moving the mouse all over the place, and we're just kind of looking at her, and all of a sudden, it crashed. It's like, yes! You know what it was? We had captured the mouse move event. It actually had code in there. And so she was executing that 500 times a second. We think we know what users do with our systems. No, they don't. This is my point about triggered, is the fact that what we're trying to do is simulate the user experience. But what we generate are these hotspots in the database. Maybe it's just because of the way we've structured our data that all of a sudden we're doing a lot of inserts. We go from a row level to a table level to a page level lock. Boom, test failed. See, this impacts our availability. No, the system's perfectly fine. The flaw was with our testing. So that's the negative of triggered fitness functions. But that software doesn't get released if there's a problem. Okay. Let's take a look now at continuous. Those that run in production, they're running right exactly now. Well, let's take a look at the trade-offs here. Because, folks, there's no load test to maintain. It's just capturing and measuring data. As a matter of fact, there's no data to maintain. This is actual user load, actual user behavior. It's measuring those peaks and valleys of when users are in the system and when there aren't. When we have high concurrency and when we don't. We don't have to simulate this. We don't have to maintain any test data. No, it's all there for us. Oh, that's nice. It also allows us to measure trends. Because when we do a load test, or when we do a test, it's not always load, when we do a test and a triggered, that's that instance in time. Now, I have done trend-based triggered fitness functions, which is a matter of when we test, we start recording all those results, and we continue to compare those. It's rather complicated and not quite as accurate. But I can measure trends over time as opposed to, did it work, did it not work, did it work, did it not work? Pretty cool. Well, clearly, continuous are a lot easier and a lot better, except I don't find out that we just have a problem until after it's released into production. I heard this thing in another talk called trade-offs. That everything is a trade-off. Even this is a trade-off. Yes. Triggered fitness functions, early detection, but they're really expensive and a lot of effort to maintain. However, continuous fitness functions are later detection, but we get much better accuracy, much better results, and they are a lot cheaper. Wow, that is a hard decision to make. Actually, it's really not. That's the trade-offs. Okay, so the point is this. How do I make this decision now? It's actually rather straightforward. If we introduce a structural problem, don't forget, these are not unit tests to test functionality. We're not testing functionality. Does the user get the right question? If they submit question 20, do they get 21? That's a functional test. When I grade it, I need to test the grading process. No, I'm not testing functionality. I'm testing structure. If we introduce a problem of performance, of scalability, of responsiveness, of availability, is it okay that that gets released into production and that we can fix it in the next iteration or next release? That really is the question. Can we afford to do that? If you're working on a medical system for a life support system or something like that, the answer is no. Those would absolutely be triggered fitness functions. Yeah. If I've got an order entry system where I'm placing orders for books, other kinds of products, can I afford an iteration, whatever size that is, to be able to fix that? Yeah, I probably could. It's the nature of the domain that helps us decide between these two. Okay, so let's actually write them now, because now that's what those fitness functions are. So here's our student test-taking system. Okay, so what can you imagine are the fitness functions we can write? I can give you a hint. Students are taking a test. We can have up to 200,000 students taking a test at the same time. Some days, we only have 20. Some days, it's up to 200,000. That's elasticity. It has to be fast enough. These are timed tests. If the system is too slow, no student will ever be able to complete the test. A directive from the education department. It is absolutely imperative, 100% imperative, that no student answers are ever lost in the system, ever. Regardless of what happens, I don't care. We cannot ever lose a student answer if they answer question 4 is B, and they hit submit, and we deliver the next question. Never can that be lost. That's data integrity. Okay, so let me show you the basic flow, and then let's write some tests. Okay, so what happens first is that the test taker, that's this service right here, this test taker, receives the student answer, and what it does, it sends it to a queue, persistent queue, and then delivers the student the next question. Let's see, here's the question. It's B. I hit enter. Boom, from the user interface, goes to the test taker, queue it, next question. Okay. The second thing that happens is while that's happening, asynchronously, the auto-grader service dequeues that answer and checks to see if it's correct or not. And then, the third thing it does, it writes it to the student answer database. Okay, so I did mention 3 critical characteristics that if they're not supported, this system will crumble to the ground like that bridge. So let's talk about the data integrity. There can never, ever, ever be an answer that gets lost in this system. No matter what we do, no matter how many changes occur, never, never. And let me sweeten the deal. If there is, you'll probably lose your job. Oh boy, okay. How would you verify that? That's called a fitness function. That's a test. Isn't it interesting? This is not a functional test. This is a structural test. Well, I suppose we could do this. We could do kind of an old checksum pattern. Checksums are really useful. In other words, here's what I can do. I can fairly straightforward. I can measure and record the number of student answers that are received from the user interface. I'm test taker. Yep, I'm getting all these. Every time I get one, I stream that out to Kafka. Yep, I received this from this student, this one from this student. Okay, I can just stream that. I've got that information. I can also record the number of answers that the grader receives. I received an answer, let me stream that. Now I work on it. I received another answer, let me stream that. And also, I can actually do a query and count how many answers for that test session actually made it to the database. Let's check some. I can compare all of those. Well, that's kind of a basic, straightforward, easy fitness function. Is it? What's the problem with this fitness function? Think about the flow in the system. If I'm constantly measuring this, what's the problem here? What's that? Yeah. These will never equal each other, will they? This is asynchronous. Test taker now has 25 answers. How many are in the database? 23, because they're still dequeuing and grading. Yeah, this is why some of these are fairly complex. Uh-oh. Well, that won't work. We'll see fails all the time. They'll never equal each other. Or will they? When do they finally equal each other? When testing is complete. That's when we measure it. This is a continuous fitness function running in production. But do you see, when I do that metrics gathering or the analysis, I wait until testing is complete. In other words, are there any students signed in? Nope. Good, that means we're not expecting any new answers. How many grades are in the queue? That's the queue depth. 0. Good. Autograder, are you in an idle state? Nope, still have an active thread. Okay, we wait a little bit. Autograder, are you in an idle state? Yep, no threads. Now I can execute that. All of those things, by the way, can also be part of observability. Student sign-in service knows, holds the session ID. It knows when there's no session IDs. It knows when all students are signed off. That can stream that information through observability. So do you see, this is why tools are useful, products. But no product in the world is going to tell you all of this information. Yeah, we have to actually stream that ourselves. That's what observability is. Okay, and we do this. So for each testing session, that's when all the students sign in from various regions around the country, and then all of a sudden testing stops. Maybe it's 5 p.m. And this is what it's analyzing. Every day it's going through, and you notice all 3 of these are always equal. That demonstrates no data loss. We have high data integrity. No, we don't. Good thing we had these fitness functions running because we were doing good. But look at this testing session right here. Submitted. Graded in the database were the same, but I had submitted more than I actually graded and put in the database. We lost a message. That is when I get notified. I didn't on these days because the submitted versus graded versus database are all the same. Oh, that's a cool fitness function. So that's kind of a student answer checksum. What about elasticity? Can you support 200,000 users? Sure. Are you sure? Reasonably sure. Let's write a fitness function to actually track that, because maybe you can now, but what about after 4 iterations of changes? Does it still support 200,000? What's the trend? Is it getting worse or better over time? What can we do to measure this? This is what it's about, writing tests for architecture. The first step is a thought process. I've got services here. I need to make sure that we can process all those users. Now, what would it mean to test elasticity? What does that really mean? A, when we get up to 200,000, does it crash? No. What's another one we can do, though? Because that's an easy test. Did the system come down? Yes, then it's not elastic. But what's another one to see if it's getting better or worse? Yeah. If I've got 20 students, what's the response time to be able to give them the next question? What if I have 200,000? Does that change? That's how you measure scalability and elasticity. So let's do that. Okay. So first thing we're going to do is response time analysis. I can do this. I can actually capture and measure the response times along with the request timestamp from the student sign-in service, because I've got multiple elasticity parts. It's not about all taking a test. It's about everybody signing in at the same time. I can also do the same thing in the test taker. Now, if I capture this information, you know what else it gives me? Because I'm capturing the student ID? It gives me the number of concurrent users also at that particular point in time. And so I can record those response times. And I can measure a fitness function simply just to start tracking those as a function of each other. That's the easiest fitness function you could write. This code would all be in that analytics service, by the way, not the capturing piece. The capture is just, every time something's sent to Kafka, I get it. Yeah. So now, let's write that. And here is what that graph looks like running in production right now. This just continually runs. I mean, if it's idle, it just goes down to 0 and then spins up. But you'll notice what happens. Look at the trend here. Here's the number of users, number of students signing in or taking a test, and it's continued to increase. This school over here started taking a test. Over here, maybe an hour later, they started taking a test. An hour and a half later here, 20 minutes later, you guys start up. And so you notice we're starting to increase to that 200,000. But do you notice what happened to our average response time, average duration of delivering the next question? Because we don't want that student to wait. It kind of went like this. But what that code is actually doing is it's taking every data point and recalculating the standard deviation. And it's measuring that standard deviation to 1, maybe 2 standard deviations from the norm. It's continually measuring that trend. And if we do that, you can kind of see that pretty much all these response times are about within 1 to 1.5 standard deviations from the average. That demonstrates, proves a scalable system, an elastic system. But you notice, we had a little problem. Now, this is not something I'm looking at. I mean, I could have it generate graphs and put them up on the screen. That would be kind of cool. But this is all just the behind-the-scenes things that's going. But look, we had a little problem here, didn't we? Then all of a sudden, those average durations started climbing. Students were waiting a little bit longer to get that next question. It's like, come on, I just answered that one. Come on, I've only got 2 minutes and I've got 15 questions, come on. But notice what happened here. We were not too bad, and all of a sudden we got a spike right here of students signed in and starting to take a test. So likely the explanation was that the system recognized this and started new instances of the test taker. Whoops, we got some more load, create some more instances. That's an elastic system. And then they all started. And so there is a good explanation of why that little graph went like that. Now, we could research that, but I don't care. I don't care. Because that's what's happening in that analytics service. It's looking at all that. It may give me that for information, but I'm not notified. I'm looking for the trend of that. It's a pretty neat fitness function. All right. How else can we do this? Now, I mentioned that those test-taking applicators, blah, blah, blah. The explanation of that was that it was starting up new instances of our test taker to receive and deliver new questions. Well, I can measure also how long it takes to start those up. That's mean time to start. Because if we start adding functionality and it starts taking longer, all of a sudden, boom, crash. So let's measure that. How can we do that? Each instance can absolutely measure the time it takes to start up. As a matter of fact, this is information we can get from things like Kubernetes, for example, or any service orchestrator or app server. How long did it take to start up an instance and have it be immediately operational? And write a fitness function for it. And as a matter of fact, let's write it, let's do it, And here we go. Are you ready? This is just running in production every day. That's the mean time to start. So we can see that it's not consistent. What happened right here on this day? Boom, I got notified, by the way. What happened? That was last night's release. Somehow we added functionality or did something in code to that test taker service, and now we've doubled the time it takes to start. That's bad because it's not going to be as elastic. So what do? Let's find the problem. There it is. Let's reverse those changes, put them somewhere else, and guess what? That was that release that day. We went back down to where we were before. How would we ever would have known this if we didn't have fitness functions? You know, there's a third and final way we can actually measure elasticity here, and that's actually to do throughput analysis. Because where's another potential bottleneck here? Oh, I've just proven that our test taker right here is elastic. But we have another bottleneck, don't we? Because if the auto grader is too slow, which is asynchronous, these queues are going to fill up and crash. Boom! And I can no longer submit answers. We forgot about that part of the system. And you know what? This is easy to forget about. Oh, that's all back-end. That doesn't have to be elastic. Yes, it does. Because we have a bottleneck point right at the queues. So, what do? I write another fitness function. By the way, I write a lot of fitness functions. And you know what? These are actually quite fun to write. It's a nice change from the boring business logic coding we have to do. It's actually quite fun. Anyways, to measure the queue depth. How many messages are in the queue at any given point in time? Maybe every second, every 5 minutes. Let's write a fitness function for that. And let's run it. And here's what it looks like. Isn't that interesting? This is all just capturing data, analyzing it over time. That's pretty good. Because if we now start measuring a standard deviation, that's a pretty flat line. That's what we're looking for. This is basic mathematics in this analytics service. That's exactly what it's doing. That line that I drew there has a slope. And that's what it's measuring. It's measuring slope. So the increase in slope tells me I've got a trend. Let it go for a little bit. Let's keep lowering, because maybe it's just an anomaly. Nope, that slope is continuing. Same slope, but it's continuing a long time. Now, notify me. Now, so that's all these analytics services. That's a fitness function. That's how you measure that kind of thing. All right. Well, listen, we've got about 15 minutes left, and now we can look at another type of testing. So that's all operational. You know, is it performing? Is it scalable? All that kind of stuff. But what about the overall structural integrity of that system? Is it clean architecture? Is it sound? Is it going to fall apart even though it scales? Because a lot of systems do. Okay, let's measure the structural integrity. So here's an example. These are all my components. I've got an order placement, and that's its namespace, app.placement, whatever. I've got inventory, supply ordering, email notification, and item pricing. Well, what happens when I place an order? Well, the order placement gets that. Now, I have to decrement the inventory. Is it my responsibility to decrement the inventory? No. So what do? I tell inventory management to do so. I mean, if that's a service, I would invoke a service, a RESTful call. If that's code inside my application, that'd be a monolith or a large service, that would be instantiating a method within this namespace or directory and invoking a method in that class, instantiating the class and invoking a method there. So it doesn't matter. These could be services. These could be components within my system. What else happens? Well, I also have to notify the customer. Is it my responsibility as order placement to notify the customer? No. So I go tell email, hey, notify the customer. Okay, fine, I will. Now, 2 other things happen, though, in our system. You see, when we place that order, if the stock goes too low, I need to know to order more stock from the supplier. Is that my responsibility? No, it's supplier ordering. So I tell it, go do that. We also do something a little, well, not so good. Because if the inventory amount goes too low, you know what we do? We increase the price. We've only got 4 left in stock. Increase the price 20%, because now we know you're going to buy it. Oh, there's only 4 left. I got to wait, the price just went up. This is what airlines do, by the way. Why am I saying shh? We all know that. I mean, 2 months ago, the seat was 3,400 rupees. All of a sudden now, today, it's 6,900 rupees. What happened? Because there's only 2 seats left, supply and demand. But is that my responsibility as order placement? No. So I tell item pricing to do it. Do you see a problem with this architecture? Yeah, that is highly coupled, isn't it? Yeah, that has the highest level of efferent or outgoing coupling of any component. Yeah, that's tight coupling, everybody. Yikes. If these were services, what that means is I can't place an order if the supplier ordering service is down, because I'm dependent on it. I have to have item pricing available. So let me show you how to fix this problem. It's something called the law of Demeter. Now, the law of Demeter is called the principle of least knowledge. It's based on, and it's named after the goddess of Demeter. And this is in Greek mythology. The goddess of Demeter was the goddess of agriculture, the goddess of grains. And she, in mythology, produced all the grains for all the world. Everybody had grains. They did different things with them. But the goddess Demeter had no idea what you did with those grains. That's where it gets its name. Principle of least knowledge, highly decoupled. The goddess of Demeter was not coupled to you at all to make your bread. Okay, so let's see how this works. A service or a component should have limited knowledge of other services or components. Okay, that's just called loose coupling. Well, we all know to strive for loose coupling, but no one tells us ever how to do it. Now, I'm going to show you how to do it using the law of Demeter. Okay, principle of least knowledge. Okay, there's 3 rules. Rule number 1, don't talk to strangers. Rule number 2, only talk to close friends. Rule number 3, only talk to those related to you. Has anybody heard those rules before? The answer is yes. Every single one of us have as a child, because this is what our parents told us. When we go running out the door, don't talk to strangers, only talk to your close friends, only talk to your relatives. Yes, these are the guidelines we've been given. Who knew? Even us as parents say that to our children. Who knew all this time we were actually executing the law of Demeter? Anyways, let's see how this works. The principle of least knowledge. Okay. Order placement to supplier ordering. Am I responsible for ordering more stock? No. That's part of that component or service. Are you ready? Should I even be responsible for knowing that we have to order more stock? Principle of least knowledge. The more I know, I, being order placement, know about the system, the more coupled I am. The least amount I know about the system, the more decoupled I am. No, I shouldn't even know that we have to order more stock. Can I delegate that knowledge to somebody else? Sure, inventory management. Let's push it over there. So I do. I have less knowledge, don't I, in the system? I have less coupling, too. Isn't that amazing? That's the law of Demeter. Same thing. Should I know that I have to increase the unit price? I don't know. Can I delegate that information to somebody else? Yes, I can. Inventory management. Guess what I've done? I've just decoupled my system. These are strangers, by the way. These ones, over here. Item pricing and supplier. These are strangers. Why would you say that they're strangers? Because they're not directly associated with me. Inventory management and email are close friends or relatives. Why? I have to decrement inventory. Should I have that knowledge? Probably not. Can I delegate it to anybody else? Nope. There's no one else between us here. I can't. I could make another component, but that's silly because I'd be coupled to that. That's why those are close friends and relatives. Okay, so we have a highly decoupled system now. Congratulations. But here's the point. How do I make sure that stays the way it is? Because now I have a clean structure. I have a sound architecture. But what happens? We continue to make coding changes and add features, and this just starts going back to the way it was before. Fitness functions. I can write fitness functions to do this. And these are now where we still write code, but these are tools that are free. In the Java platform, we can use something called ArcUnit. This is free. In the .NET platform, we can use things like ArcUnit Net or NetArcTest. We can also use products that are also, well, I'll say free in parentheses because certain features are, of something like SonarGraph, for example. And that will work on a host of languages. These are fitness functions we can write. Oh, there it is, SonarGraph, right there. Yep. Okay, so let's write some. All right, now we get to write code. All right, so notice the only components order placement can talk to, are these. Order placement can only talk to inventory and email. Don't talk to anybody else. Okay. And of course it will next week. Let's make sure it doesn't by writing a structural test. And here it is. Now this is the Java version in ArcUnit, but let's read it. Placement, and let's read the actual test. Placement can only access notification and inventory. Let's read this together. Classes.that.reside in a package app.placement should .only access classes that reside in a package notification or inventory .check. That's almost English language. That's the beauty of these tools. If you could just say the rule, the constraint, the API matches it pretty closely. Yeah. Let's do a couple of these, because these are cool. I'll show you some C# ones here. Here's one. Architecture, structure. So we've got I'm going to go over to this one. It's a little easier to see. Presentation, business, service layer, persistence layer, database layer. We've got a layered architecture, very typical. Well, one of the constraints we have is only the business and services layer can talk to the database. Presentation folks over here don't access the database directly. Okay. What are they going to do next week? Access the database directly. Of course, it's faster, isn't it? Why should I go through all these layers and all this object instantiation just to query the first name of the customer? So all of you who are the UI developers say, my responsibility is to do that as fast as possible. Therefore, I'm going to go straight to the database. I'm going to bypass all of you. But I made this architecture decision because we change that clock, that database, all the time. And I want to control change through our architecture. Because now that I make a change to the structure there, what happens? Oh, the UI has to change. Yes. Well, how do I keep all of these lovely people over here from calling the database directly? I use a very big stick. And I watch over them 24/7. And if you call the database, I'm going to hit you over the head with my stick. That now won't work. That would be fun, but that won't work. All right, let's write a test for it, a structural test, an architecture test, a fitness function. And here it is. So watch this, and I'll read it here. No classes that reside in a package presentation should access classes that reside in a package persistence. Fail, because of course you're going to do it. And so what happens here? .because. I love this part right here. In that test, I can give the reason why this structural integrity constraint exists. Why? Because we have a closed layered architecture to control change. Control changes made in the database. Persistence can only communicate to the business layer because of that. Yeah, this is the same thing, by the way, in NetArch test. Types in the current domain that reside in a namespace presentation should not have a dependency on anything in my app.persistence. This is how architects code, by the way. You wonder how you become a software architect and you maintain hands-on coding? Write fitness functions. This is software that executes in production. That's pretty cool. Yes, should architects code? Absolutely. Because we're the ones who write those tests. Exactly. So, these are some of the structural integrity kind of things we can do. Hey, one more to show you, which is really cool, because we do have a layered architecture. Here's the test to make sure that we manage those open and closed layers. So here's a layered architecture. This is in the API. Yeah, we have a modular monolith. Fine. It's the same API. So here's all my layers. And those are the layers, or domains, if we're using a modular monolith. So presentation is presentation. Business is this namespace, directory structure there. And here are my structural rules. Let's read them. Business may only access layers presentation. Services may only be accessed by business. Persistence may only be accessed by business and services. Any open and closed layers I can describe in this test right here. That's pretty neat. So those are structural integrity constraints. So we've seen two kinds of tests we can write that are not functional tests. These are structural tests. These test our architecture. Is it still okay? Is it still satisfying all the needs of that system? Please, please embrace this concept. And if you do, it will help you avoid this complete mess right here. Please don't let your systems fall apart like this bridge. All right. Thank you all so much. Thank you.